These are the video notes for the first part of Chapter 14, which deals with simple harmonic motion, which is a repeating type of motion. So, and it essentially oscillates, and it oscillates in the form of either, you can call it a sine or a cosine, and the only difference between a sine and a cosine wave is where it starts. So the standard for the position graph is a cosine graph. And so this is the standard equation for the position of a simple harmonic motion. The A here represents the amplitude, so it's how big is the motion. And then you've got the cosine, and this is the argument. The biggest thing here is that we have to be in radians. So up until now we've been in degrees all the time, but now we have to be in radians. And this is, whatever time you're at, and the T here is the period. It's the time for one full cycle or one oscillation. We call that the period. And then the frequency is the number of cycles per second. So they're just inverses of each other. And you will find that this 2 pi over T, we're actually going to replace with the omega, the tush, which is the angular frequency, which is found essentially in radians per second. And so there is this is an example here. If you're looking at how high the wave goes, this would be the amplitude. If you're looking at trying to find the period, it would be the time it takes to return to its original spot. And so this is showing 2 periods of this particular motion. And so here is that angular frequency, the omega, is 2 pi over T. It's also equal to 2 pi F if you're trying to calculate. And so we simplify this argument by just having x equal to a cosine of omega t. This allows us to find where the particle is at any particular time. And we know that the cosine, the biggest the cosine can be is 1. Cosine of whatever. That's the largest value the cosine can be. And so if we're looking at the velocity of this thing, we would actually take, I'm actually going to move to the next slide. Where is it? Here. So here we take A equals cosine of omega t, and then sometimes we also have a phase shift, this phi symbol. And this just means that it's not starting exactly, it's not at its highest point at 0. It's shifted over some radians. And then to find the velocity, we would just take the derivative of this. And to take the derivative of this, this is on your, it's actually on the back side of your yellow sheet. We have to take the, whatever's multiplied by t comes out. That's considered a constant. And then we have to take the derivative of cosine, which is minus sine. So we end up with minus omega a, sine. And then the argument stays the same. So this omega t plus phi that was here before stays the same. And so this is where if the cosine of anything, the biggest it can be is 1. And so if we have our maximum velocity, the maximum velocity is actually going to be omega a. And when we can do the same thing again for acceleration, we would just take the derivative of this again. Okay, let's back up. Okay, so that's where this omega a comes from. That's the maximum speed. The negative sign would be included if we wanted a velocity and needed to know the direction. All right, so here's an example. An air track glider is attached to a spring, pulled 20 centimeters to the right, and released at time 0. And it makes 15 oscillations in 10 seconds. So what is the period of oscillation is the first part of this. And so we're going to get a pen. I like blue. Okay. So period, I'm going to do it up here, is the time it takes for so many oscillations. So I'm going to have my 10 seconds is the time divided by the 15 oscillations. And so I get 0.67 seconds. What I really want from this is omega. And omega, remember, is 2 pi divided by the period. And so if I take 2 pi divided by 0.67, then then I'm going to get 9.4 radians per second. And here the amplitude is going to be, I'm pulling it back 20 centimeters, so 0.2 meters. All right, so this was my answer to part A. For part B, the maximum speed is just going to be omega A. So this is 9.4 times 0.2 gives me 1.9 meters per second would be the maximum speed. And then the position and the velocity, so the position is just x equals a cosine of omega t. And we want to do it at 0.8 seconds, so my a is 0.2, and then I have cosine of, and I got to take 9.4 times 0.8, and then take the cosine of that value. And what I end up with is 0.014 meters. And it would come out, if it's going to it's going to be on my left-hand side or on the down part, it would come out negative. It does not. So my velocity is minus omega a cosine of omega t. I've already found out what this omega a value is. It's my 1.9. And then cosine of, again, I got to do the 9.4 times 0.8. And this comes out to be a negative 1.9 meters per second. So even though it's on the right-hand side, it is moving to the left because of this negative sign. And simple harmonic motion can be related to circular motion. If this goes around in a circle, it produces the same waves as simple harmonic motion. All right, so this is the part I was talking about where you have the phase shift, and the phase shift is just how far it's shifted over, and so sometimes you have to find that. The assumption is not that you start where you're supposed to. It's not a normal cosine wave. So the idea behind using initial conditions comes in. So an object on a spring oscillates with a period of 0.8 seconds. So I'm going to write that up here. I've got t equals 0.8, which means omega is, remember, 2 pi over t, which is going to give me 7.9 radians per second, and we have an amplitude of 0.1 meters. Now, it tells us that at time 0, it's 5 centimeters to the left, and it's moving to the left. What are its position and direction of motion at t equals 2 seconds? And so in order to find, remember that x at any time, so for this part at x equals 0, I would do a times the cosine of omega t plus the phase shift. But if t equals 0, this disappears, and it tells me that at x equal, or at time 0, where this thing is. This is at negative 0.5, and this is 0.1, and then I just have the cosine of phi. And so if I want to find the angle, I just take the inverse cosine of negative 0.05, sorry, it's 5 centimeters, 0.05, divided by 0.1. And having found my calculator, inverse cosine of negative 0.5 divided by negative 0.05 comes out to be 2.09. That's my phase angle. 2.5 radians is the correct unit for that. So that's what phi is. Okay, and so now I want to know the position. So x equals a cosine of omega t plus the phase shift. And so I'm going to have 0.1 cosine of, my omega was 7.9 times 2 plus 2.09. And so just so I know what that value is, that is 17.9. Okay, so that omega t plus, and so now if I take the cosine of that and then times 0.1, I get 0.057 meters. And it's positive, so it's over on the right. And then I can do the same thing here for v. It's minus omega a cosine of omega t plus phi. So I've got minus 7.9 times a, which is 0.1, times the cosine of omega t plus phi, remember we found was 17.9. And so if I do again cosine of 17.9 times 0.79, negative 0.79, I get negative 0.46. So again, it's on the right, but it's now moving to the left. And that would be how you use initial conditions to find the phase angle up here. I think the rest just walks it through and gets you the same responses. Okay, and that's where we will end.